Welcome to Probability and Statistics. We are in Chapter 9 of William Navidi's Elementary Statistics, 4th edition. We are just looking at the first four sections, 9.1 through 9.4. There are three other sections in this chapter that I don't go through in this lesson. But if you are interested in looking at those, you can certainly do that. So, in the previous lesson, I walked through how to find a confidence interval. And again, a confidence interval is just a range of values that we have a certain level of confidence captures a true mean or proportion of some value for a population. So, for example, I might find an interval of 380 to 420, and am 95% confident that that range of 380 to 420 captures the actual average weight of an adult dolphin or something like that. In this and actually the next two lessons, we are going to look at what is called hypothesis testing, or sometimes called significance tests. A hypothesis test works in that we start with some kind of predetermined value. Maybe it's a value that has been long believed to be true. Maybe it's something that we have based on previous research or evidence. And now we're beginning to question whether or not that value is accurate, or maybe it's a productivity type value, and we're wanting to implement some new procedures in our production lines or some new training and we want to see if that training, if those new procedures are actually increasing productivity, decreasing costs, whatever it might be that we're looking at. So a hypothesis test basically takes data and looks at that data to determine, is there evidence for or against the previously held value? Let me give you an example. We have long believed and held to the fact that the average body temperature for a healthy adult is 98.6 degrees Fahrenheit. Now, I'm not saying that that's right or wrong. I'm just saying that's what we believe, right? The temperature, body temperature for an adult is 98.6 degrees. But I'm a nurse, and maybe as a nurse, I'm responsible for taking temperatures for the patients as they come into the clinic. And obviously, a lot of those patients are sick, or their bodies aren't working right. And so that's going to affect body temperature. But even for the patients who are healthy and they're just coming in for their routine physicals and checkups and things like that, that even their body temperatures just seem to be less than 98.6. And I start to wonder and start to hypothesize this idea that maybe the actual body temperature isn't 98.6. Maybe it's something less than that. And so what a hypothesis test would do is start with that kind of a premise. I would collect data. Maybe I go out and sample 500 or 1,000 healthy adults. I get their body temperatures, and I analyze that data to determine whether or not I have convincing evidence that the temperature has actually decreased or is lower than we thought, or maybe that evidence shows that I don't have reason to believe that it's not 98.6. So that's what a hypothesis test does. What we're going to look at in this chapter is specifically hypothesis testing for one sample scenarios where we're either looking for a mean or a proportion. In future lessons, we'll look at two samples, same thing, mean and proportion. And then we'll also look at multiple samples and how we handle that situation. So with that, let's go ahead and let's take a look at this. I will say that as we go through this, there's going to be quite a bit of setup before we get to the actual hypothesis testing. And the reason for that is just very simply that it is a big idea, and it was particularly a big idea in an introductory stats course like this. And so I want to make sure that I give due diligence to making sure that we understand not just the how, but kind of the what and the why that's involved in doing this. So with that, let's go ahead and take a look. So we're going to start with a couple of definitions. So let's just start with these hypotheses, because this is what sets up the foundation for this test. Again, I have a belief, a hypothesis about a situation. And so we have two hypotheses involved when we do a test like this. We have what's called the null hypothesis, and we have the alternate or alternative hypothesis. The null is, again, kind of that preconceived, predetermined value that we already have. So it states a parameter. So states that a parameter, remember, parameter is just a value that points back to the population. It could be a mean, a standard deviation, a proportion, whatever that might be. So it states that a parameter is equal to a specific value. Now that's pretty generic wording, but again, that value is something that we already have. We believe that we've known that the body temperature is 98.6 degrees. Now we're wondering if it's something different. Our null hypothesis would state that it is equal to 98.6. The way that we write this symbolically is H sub 0 for hypotenuse null or null hypothesis. And then if it's a mean, for example, we'd say that the population mean mu is equal to some initial value. Or if it's a proportion, we might say that it is P equals some initial value related to the population. Okay. So again, this would just be the H sub 0 is what we use for null hypothesis. The mu is in this case, specifically mean of the population. And then this would be the initial value that we are given, for the population. Okay. And then same for the proportion. All right. So that's the null. And then we have the alternate or alternative hypothesis. And this states that the value of the parameter, differs from the null, differs from H sub 0. Now, by differs, there's three different ways we could look at that. So let's talk about what that looks like. So we're going to use H sub 1 for the alternative. So H sub 0 for null, H sub 1 for the alternative. You will see in some texts H sub A for alternative. Either one would certainly work. And in this case, then the alternative says that the actual mean is maybe greater than the initially believed value, that the mean is less than the initially believed value, or that it just simply is different from the initial value. Okay, so again, in the case of the example that I gave before, body temperature, if I'm noticing that a lot of temperatures seem to be less than 98.6 degrees, I would set up this middle alternative hypothesis to say that I believe the alternative is that the mean is actually less than 98.6 degrees Fahrenheit. Okay, so that's how we set up the two hypotheses. So just as some examples in context, let's take a look at these and set up their hypotheses. So a food manufacturer throws out 6% of its product due to worker errors. The plant manager believes a new training program will decrease the amount of waste. State the null and alternative hypotheses. So again, we would have the null, and notice we're dealing with proportions now, right? Percents or proportions. So we're going to say P equals 0.06. That's the initial value given to us. So right now, 6% of their product is tossed out due to error. And they want to put in this new training program to see if they can reduce that amount. So they run the program. Maybe 3-6 months later, they take another sample, or they look at their data to see what's changed. And they're believing that that new proportion now is less than 0.06, that they've made a difference in decreasing the amount of weight. So those would be how we'd write the two hypotheses. Just by coincidence, I didn't necessarily mean to, but another proportion problem. Principal of a high school reports that its graduation rate is 93%. The superintendent believes it's not 93%. State the null and alternative hypotheses. Now, in this case, if the superintendent were to come back and say, no, I don't think it's 93%, we would probably assume that the superintendent thinks the principal is overstating the result, that it's actually less than. But we want to be true to the wording here. It just simply says that the superintendent believes that it is not 93%, that it's something other than 93%. So when we write our hypotheses here, our initial is that it's 93%, 0.93. The alternative then is just simply that the actual proportion is something other than 0.93. So we don't want to read into this too much and say less than or something like that. It just simply says he believes it's not 93 degrees, which is basically saying that it's something other than. It might be less than, might be greater than. So that's how we write hypotheses. So with that, now let's talk about the overall process of doing one of these tests. So in this case, again, we start by stating those hypotheses, and we always assume that the null is true. Okay, so we're going to assume that whatever that null is, we're starting on the basis that that is true. We gather evidence. We take, we randomly sample. We get data to determine if there's sufficient support, and that idea of sufficiency is important. We often talk about it as convincing evidence in statistics. Is there convincing evidence for or against the null? Is our evidence overwhelmingly pointing us one way or the other? And then based on that, we make a conclusion. So one of the conclusions we might make is that we reject the null, that there is convincing evidence for the alternative. Or conversely, we might come to the conclusion that we fail to reject the null, that there's not convincing evidence for the alternative. Okay. Now, when we make these conclusions, we're not making these emphatic statements. We're not making these absolute statements about, yes, the body temperature is absolutely 98.6 degrees Fahrenheit, or no, my evidence shows that clearly it is not. It is absolutely, you're right. We don't go there. What we do is we are simply saying that the evidence is pointing us strongly, very strongly, one way or the other. And the reason for that is when we do a hypothesis test, there's always the chance for error. There's always the chance that our data is incorrect, that maybe we just got a weird sample, that something happened that isn't actually true for the situation. Which is also why a lot of times in research, you'll hear things about either large sample sizes or replication, where we want to be able to repeat that research project multiple times to see if every time we perform it, we're getting the same results over and over and over again. But again, sometimes we don't, and that leads to errors. And there's two types of errors that we can make. There's a type 1 and a type 2 error. Type 1 error just simply occurs when we reject the null, but the null was actually true. So again, going back to my body temperature example, the body temperature is actually 98.6 degrees, but my evidence points me to believe that it's not, that it's something other than. That would be a type 1 error. Type 2 error then is just the opposite of that, where the null is false, but I don't find convincing evidence to the contrary. The body temperature is not 98.6 degrees, but my evidence doesn't give me support that it's something else. I don't have reason to believe it's not 98.6, so I fail to reject the null. In other words, I reject the alternative. Okay. And so the little chart there kind of just puts that into a little bit of a visual. Again, when the going across the top for reality, the reality is that the null is true, but we reject it. That's a type 1 error. The null is false, and I failed to reject it. I should have rejected the null, but I don't. That's a type 2 error. So consider our justice system. Now, I'm not going to make any statements about how well it works or anything like that, but in its purest sense, the way that our justice system was set up to work is that when the state brings a case against an individual, accuses them of theft or murder or whatever the crime might be, it's up to the state to prove that that person is guilty, right? So that person comes in, and the assumption is that they are not guilty. That's our null hypothesis, and we assume that that is true from the outset. The state then piles on all of its evidence in an attempt to give convincing evidence to the alternative, that the person is in fact guilty. And so here, in terms of error, because there is absolutely error in our justice system, we know that. If the person is not guilty, but the judge or the jury comes back and says guilty and sends an innocent person to jail, right? That's a type 1 error. We've got a problem, right? We just sent an innocent person to jail. They shouldn't be sitting in there. On the flip side, the person is guilty. The state fails to present enough evidence to the contrary or to show that, and the judge or jury says, no, we don't have enough here to say they're guilty, and that person walks away free. That's a type 2 error. Okay. But we start with that premise of the null, that the person is not guilty, and then we take the evidence and use the evidence to see if that evidence is enough to reject the null and give us reason to believe the alternative is true. Okay. So that again is just kind of the idea. The actual probability of a type 1 error, and we're going to get more into this idea in just a little bit, so this won't make complete sense necessarily, but the probability of a type 1 error is equal to what is called alpha. And alpha is the significance level that we use when we do these tests. So with confidence intervals, we used a confidence level. We used like 90%, 95%. And when we created our interval, we were that percent confident that our interval captured the true mean or proportion. Alpha works the same way for a hypothesis test. The difference is that here we're setting, instead of setting high numbers like 90%, 95%, here we're doing just the opposite. We're setting very low numbers, 5%, 1%, 3%, 10%. And we're trying to, in order to reject the null, we have to get what's called a p-value less than alpha. Okay. So I know this doesn't make total sense right now, but just kind of know that when we talk about what's the chance of actually making these errors that we're talking about, well, the probability of a type 1 error is alpha. It's this significance level. The probability of a type 2 error gets into what's called power. And that's actually it's actually the last section in chapter 9 that I'm not going to go through. But if you're curious to know about power and type 2 errors, you could certainly look at 9.7 to get that information. Okay, so let's run through and talk then about the actual steps, the process that we're going to go through to do a hypothesis test. So when we do this test, we start by, again, well, first of all, we start with assumptions. So remember we had assumptions with confidence intervals. We also have the same assumptions here. So in order to do a hypothesis test, in the way that we're going to do it, we have to make sure that the sample is random, and we have to make sure that the sample size is greater than, and I'll say greater than or equal to 30. Again, this is the central limit theorem. It's more generically just stating that if your sample size is large enough, we can assume normality, right? This points to the idea that our distribution is normal. So if we can't say that it's normal, then we can't actually use this process, because this process is designed only for distributions that are normal. Now, does that mean that if it's not normal, we can't do a hypothesis test? No, there's just other ways then to do the process, but we're not going to get into that in this lesson, or for that matter, in any of the future lessons in this book. Okay, so we've shown that yes, it's normal. Yes, we've got a random sample. We can go ahead and do this process. Again, first thing we do is we state the hypotheses. So to just restate that again, and I'm going to do this just for mean, because that's what we're going to start with specifically, and then we'll do the same thing for proportions. So we start by stating that the mean of the population, mu, is equal to whatever that initial value is that we are given. The alternative is that mu is either greater than, less than, or not equal to that same value. That it's something different. And based on the situation, that kind of determines which of those three options we're going to pick: less than, greater than, or not equal to. The next thing we do is we choose our significance level, okay? So when we choose a significance level, again, this is basically a number that determines how difficult it is to reject the null. The smaller the value, the more difficult it is to reject the null. Larger value, easier to reject the null. So based on the situation, you want to pick an alpha value that makes sense. If I am, if there's a long-held belief that the average weight of an Oreo cookie is 8 grams, and suddenly I'm believing, no, I think that the weight of an Oreo cookie is actually less than 8 grams, that's not really a life-changing, life-altering, situation. If I'm really intent on trying to prove that the average weight of an Oreo cookie is less than 8 grams, I'm going to set a high alpha, right? I don't need to make it real difficult on myself to try and prove that. I just want to try and show it. On the flip side, if I'm if I'm on trial for murder and I'm looking at life in prison, I'm hoping that the jury and judge are going in with a really, really small alpha value, less than 1%, because if they're wrong, right, if they reject the null, I go to jail. And so I'm hoping that they're going to make it very difficult on themselves to reject the null. The smaller the alpha, the harder it is to reject the null. Now, typically, we use 5%. So typically, we'll use alpha equals 0.05. But again, that varies on situation. And typically, a situation, a problem would tell you what that is. If you're doing this on your own, again, you decide what you think is most appropriate. Then we have to find this thing called P, and P is what tells us whether or not we have the evidence to reject the null or not. So P, very simply, is the area under the curve. So again, we're dealing with normal distributions here, right? So let's go back to my my example of body temperature. Right now, we believe that the body temperature is 98.6 degrees, right? That's my null. I go out and I randomly sample a bunch of healthy adults, and I find that the average temperature of those adults is 98.1. The question is, was that a fluke sample? Did it just happen by chance that they were half a degree lower? Or is there something to this? Is there actually evidence to suggest that the body temperature is lower than 98.6 degrees? Well, the way that we figure that out is we just find the area, in this case below, because we're looking for less than. And so the question is, what are the chances of getting 98.1 from a sample, or more extreme, in this case, or less than, by chance? What is the probability that happened by chance? If that probability is very, very small, then we're saying that look, it was highly unlikely to happen by chance. We've got some convincing evidence here that it's less than 98.6. On the other hand, if we could show that, oh, look, like if you took that sample 100 times, 20 of those times, you're not going to get the same results. So you've got a 20% chance of getting those results by chance. Then we don't really have strong evidence to reject it all. We don't have reason to believe that it's not 98.6. And so what we're doing is we are comparing P to alpha, which I'll get to in just a minute. But what we're doing then is in this case, we're either finding Z or T. I'll start with Z. And Z, again, remember, is the value, the sample value minus the population value, divided by standard error, which is the standard deviation divided by the square root of n. Now, this assumes that your standard deviation for the population is known, that sigma is known. Okay. If we don't know the population standard deviation, then we have to find T, and we'll do that a little bit later. Then we go to the table or use technology or however you'd want to do this, and that is going to give us this P value, the area under the curve. All right. And then based on that P value, we're going to go ahead and make our conclusion. So if P is less than alpha, right, very, very, very small probability of happening by chance, that gives us the evidence to reject the null. So we would reject the null hypothesis, and we would say that there is convincing evidence, not just evidence, but convincing evidence for the alternative. Now, again, we're not saying 100%, we're not saying for sure, but we just have very, very strong, very convincing evidence for the alternative. On the flip side, if P is greater than alpha, then we're saying, yeah, there's those results could have happened by chance, and so we don't really have good evidence to reject the null. So in this case, we would fail to reject the null. Fail to reject the null, and we would say that there is not convincing evidence. There is not convincing evidence, or we do not have convincing evidence, however you want to say that, but there's not convincing evidence for the alternative. Evidence for the alternative. You notice I use H1 and HA. I'm very accustomed to both. So sometimes I will use H1, sometimes I will use HA for the alternatives. So I apologize for that. But that's the process. So we state the hypotheses, we set our alpha value if it's not already given to us, we find P, the area under the curve, and then we simply interpret the value to determine whether or not we have convincing evidence for or against the alternative. So let's put all of this together now, and let's actually look at an example of how a hypothesis test works. So the national mean score on the math test of the ACT is 20.7 with a standard deviation of 5.4. A large school district wonders if its students outperform the national average. The district randomly samples math test scores for 100 students and finds that the mean of the scores is 21.5. Can the district conclude that its students do better on the math ACT test at the alpha equals 0.05 significance level? Okay, so national average is 20.7, standard deviation 5.4. The school's students average 21.5. If you just look at that on face value, right now there is evidence that the school does better, right? Their average is higher than the national average. The question is that average enough, or is the data enough to show with convincing evidence that the school outperforms the nation? So that's what the hypothesis test is going to do for us. So again, when we do this, we're going to start with those checks. We want to make sure that our sample is random. And in this case, it does tell us that they were randomly sampled. So we do have random sample. And we want to make sure that we have a large sample size. And it says that they sampled 100 students. 100 is certainly greater than or equal to 30. And so we can say, yep, by CLT, that we can assume our distribution is normal. And because it's normal, we can go ahead with this process. So with that in place, let's go ahead and write our hypotheses. So in this example, mu is, again, the national average of 20.7. And the school believes that their students are doing better, that their scores are greater than 20.7. And we are going to test this at the alpha value of 0.05. All right, so we've done our checks, we've set up our hypotheses. The next step now is to actually work towards finding P. So to find P, in this case, we're going to find Z first. Let me draw a picture here and just remind us of what we're doing on this. So national average, mu, is 20.7. The school district's scores average 21.5. And we're wondering, what is the probability of getting that score or higher just by chance? Was this, again, a fluke sample of 100 students, or is this typical? And if it's typical, is it enough to show that the school outperforms the nation? So that's kind of our picture. And what we're looking for is this area here. This is going to be our P when we find that area. So Z, remember, is the sample value, 21.5, minus the mean of the population, the parameter, 20.7, divided by the standard error, which is the standard deviation of the population, divided by the square root of 100. And if we were to put that into a calculator, we would get 1.48. Let me rewrite that. It's a little sloppy, 1.48. Okay, so based on that, I'm not gonna show the table. You know, if you need to see that, you can reference the previous video or just find a video on how to use a significance table. But if we were to look in the table for a z-score of 1.48, we would find a value of 0.9306, or about 93.06%. That's the area under the curve. Except that when I look at my picture, which is why I love to draw pictures for problems like these, that is clearly not the area, because 93.6 or 0.06% would be most of the area under that curve. Remember that if you are using the table, your table only finds values to the left, not to the right. So to find the actual p-value, the area under the curve, we have to do 1 minus 0.9306, which is 0.069 if we through rounding and things like that. Okay. All right, so that is our p-value. We take the p-value, we compare that to alpha. And in this case, because p is less, or excuse me, is greater than alpha, right? Not infinity, alpha, right? P is 0.069, alpha is 0.05, p is bigger than alpha. That means that the likelihood of those scores happening just by chance is not uncommon enough for us to prove or give evidence for the fact that the school does better. So in this case, we fail to reject the null. We fail to reject the null. Whoops. I was going to say to reject again. We already said that. All right, we failed to reject the null. We could say something like, there is not convincing evidence. There is not convincing evidence that students at this school outperform the nation, or I'll say the national average, on the ACT math test. We always want to give context when we're writing our conclusion, because that's the whole point, right? Is we're doing this with purpose, with context. So on the ACT math test, okay? Now, again, do we have evidence? Yeah, they did score higher than the national average, but the key here is we don't have convincing evidence. There's not enough there to put into some journal with authors' names and publications and things like that to say, yes, we have convincing evidence that our students do better. They maybe do, but we just can't say that with certainty. So that's how how a hypothesis test works. Okay, let's do one more, and then we're going to get into what it looks like when we don't know the standard deviation. And as always, when I do these videos, I like to encourage you to stop the video and just try these on your own, see if you can do it, and then you can just start up the video again to see the solution. So it says a large company regularly measures the job satisfaction of its workers through a standardized survey. Scores range from 0 to 100, with higher scores reflecting a higher satisfaction. The mean score overall employees is 74, with a standard deviation of 8. A new telecommuting policy allowing employees to work from home one day each week was recently implemented by the company. Shortly after, a random sample of 80 workers was given the survey to determine if job satisfaction had changed since the policy was put into effect. The sample mean was 76. Assume sigma equals 8. Can the company conclude that the mean level of satisfaction changed at the 5% significance level? Okay, so again, we've got these this employee survey. Initially, the mean score was 74. They put in a new policy. They say you can now work from home one day a week. Sometime later, they come back and they do another survey to see if job satisfaction has increased. And the mean of that new survey is 76. So again, is there evidence that job satisfaction has improved? Yes. Is it convincing evidence? Well, that's what we need to determine. So again, we're going to start with our checks. And we always want to check for random sample, and they tell us that it is a random sample. We want to check to make sure that the sample size is large enough to show normality. And they say it's a random sample of 80. And so, yes, we've got 80 is greater than or equal to 30. So by CLT, we do know that this is normal. Remember, this is always pointing to the fact that we have an approximately normal distribution. That's what we're looking for here when we do that second check. Okay, so we can go ahead now and do our process. Our null is that the mean is 74. That was the initial value. Our alternative, again, we're wondering if those values have changed. Now, in this case, we would assume that we're looking for greater than. Okay. But notice that in this case, it just says, can the company conclude that satisfaction changed? Not got greater, not reduced. Did it just simply change? So, as much as I want to put mu greater than 74, because that makes sense to me in this problem, they just want to know, did it change? Now, maybe they're concerned that being home one day a week is actually not the right decision. Maybe these employees love to be with each other and they love to come to work and kind of have that social interaction and work in teams together and things like that. Maybe satisfaction actually went down. Now, that's not what our data is suggesting with a score of 76, but it's possible. And so we're just going to look at, is it different? And again, we're going to use alpha equals 0.05 here. All right, now again, because we know the standard deviation for the population, we're going to use Z. In the next example, we're going to flip that and assume that we don't know and you start to use T. But we'll use Z here. So again, Z is going to be the sample minus the 74 divided by the standard deviation of 8 divided by the square root of 80. And that gives us a Z of 2.24. Okay, now let me draw a picture before I go any further here, before we get into the actual table stuff. So again, 74 was the mean, 76 is the new result. Okay, so if I think of this in terms of standardizing, right? When we find Z, we have done what's called standardizing the value. That changes the mean to 0. This value is now 2.24 relative to that. Again, this is what we would think we would be looking for, is just the greater than, right? Did morale improve? Did job satisfaction improve with that change? But because we're looking at a not equal to, we actually want to look at both sides of the graph. So I also want to look from negative 2.24. So symmetrically, the same area on the other side of that graph. This is what we call a two-tailed situation. And when we've got a two-tailed situation like this, we have to double our p-value before we test against alpha. Okay. So in this case, I'm going to take the 2.24. Now, I could take 2.24, but that's going to give me to the right. The table gives to the left. So the other thing I could do is, rather than look at 2.24, I'm going to look at negative 2.24, because negative 2.24 is going to give me this area to the left. So from the table, when I look up that z-score, I'm going to get 0.0125, which means that this area is 0.0125. But it also means that because they're symmetric, this area is also 0.0125. Okay, so my p-value is that value times 2, one for each side. And in this case, p then is 0.025. Now, in this case, it didn't matter. Multiplying by 2 still does not put us over the 5% threshold. So in either case, because p is less than less than alpha, because p is less than alpha, we again, in this case, we are going to reject the null. So we reject the null. So I'll just say we reject H sub 0. I was going to write out null hypothesis, but that's easier. And so in this case, there is convincing evidence. There is convincing evidence that job satisfaction has improved. Job satisfaction has improved since the policy went into effect. Now, I'm being very careful in my words here, into effect, because I'm not saying that that the policy caused the job satisfaction. Depending on how they structured this, how they looked at their data, how they went about this, maybe we could make that causation known. But right now, there's correlation, right? The fact that the job satisfaction did go up, and it's kind of a before and after of the policy. Yeah, we might jump to that conclusion, but we don't actually know. There could be other things going on at that same time that actually caused that change in job satisfaction. Um, Whoops, and I have to go back a minute. I was just looking at my notes here, and I note or not, what I wrote here, and I noticed this should actually be not equals. Or I'm sorry, this is less than, right? Um, and well, I just totally messed myself up here. Sorry about that. I was looking at the less than. I was going to change it to not equals, but that's just simply that job satisfaction. This is what I need to change. Not that it improved, but it is simply has changed, right? That's something didn't feel right there. It has changed since the policy went into effect. Okay. All right, but the point I was making before is we don't know for sure if it was the policy. Maybe the employees just found out a week before the survey that they were all getting raises or bonuses. Maybe the weather changed and suddenly got like warm and sunny out, and so they're in better moods because of that, right? It could be any number of things, and so we want to be careful not to attach causation to a situation like this. All right, well, let's move on now to a problem where we don't know sigma, we don't know the population standard deviation, and look at how we handle that. So here now we have to use t, and the formula for t is almost identical. It's the sample mean minus the population mean, and then we divide that by the not the standard deviation for the population, but the standard deviation for the sample, divided by the square root of n, or the sample size. And with this now, we also need df, which again is the sample size minus 1. That's a d and an f, df. Okay, so it says the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 30 randomly chosen locations along a stream. Here are the results in milligrams per liter. So our sample mean is 4.77. Our sample standard deviation is 0.939. An average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do the data provide convincing evidence at the alpha equals 5% significance level that aquatic life in this stream is at risk? So the first thing we need to do is our checks. Again, we want to be sure that we have random sampling, and we do. It tells us that it's a random sample. They measured 30 random locations, and then our sample size is 30, which is greater than or equal to 30. So by CLT, again, the whole point of this is to show that our distribution is approximately normal. If it's not, again, we can't use this process. All right, our alternative, or excuse me, our hypotheses. The null hypothesis, mu equals 5. The alternative, mu is less than 5. We're concerned that the oxygen level in the river or the stream is less than 5 milligrams per liter. We are using an alpha value of 0.05. And so finding t, we take the sample mean minus the population mean, in this case 5, divided by the standard deviation, which is 0.939, divided by the square root of 30. That gives us a value of negative 1.34, and our df is 29, 30 minus 1. Now, I'll go to the chart in just a moment here, but if we look in the chart, there are no negative values in the table. It's all positive values, and that's different from the z table. So whenever you get a value for t, you're always just going to use the positive value. So we're going to use positive 1.34. So our t is 1.34. Our df is 29. And what we're going to do now is we're going to go to the table and remind you how this works. So what I'm doing here is I'm just looking for my df first of all. I'm looking for my df of 29. And all of the values in the table, those are the t values. These are the t critical values. So what I'm doing is I'm going across until I find 1.34. So as I go across, I'm looking for 1.34. Well, there is no 1.34 specifically, but 1.34 is somewhere between 1.311 and 1.699. So it's somewhere in that range of values. So when I go up to the top, I notice that puts our p-value, our area under the curve, between 0.1 and 0.05. So that's what I'm bringing back as my answer. I don't have a specific p-value. I just know that it's somewhere between those values. And I know it's not 0.10 because my t-value is not 1.311. I know that it's not 0.05 because my t-value is not 1.699. So it's strictly greater than 0.05, strictly less than 0.1. All right, so let me take us back to the problem. So what we find then is that from the table, and again, you can use technology and other things like that to find these same values, but from the table, we know that P is somewhere strictly between 0.05 and 0.1. Regardless of what the value is, I know that P is bigger than alpha. Alpha is 0.05. I know that P is something bigger than that. And therefore, we fail to reject the null. So we fail to reject the null. In other words, we do not have convincing evidence. So even though the test results were they were 4.77, they were less than 5, it's not enough to give us convincing evidence. So we do not have convincing evidence that the DO level is less than 5 milligrams per liter. In other words, that aquatic life is not at risk. Or I'll say it this way. So we don't have evidence that, I won't write this out, but we don't have evidence that aquatic life is at risk. Okay. Might they be? Possibly. I mean, we are getting values below, but the evidence just isn't showing it. Also possible, again, that we made an error, right? And that is always a possibility. So again, especially being as close as it is to 5, we might want to test another 30 samples, do this again and see if we're getting the same results, see if we're getting the similar results that we have here. Okay, so let's do one more. Again, I'd encourage you to pause the video, try it on your own, see if you can do this. Otherwise, I'll go through it with you here right now. So the National Institute of Health, or the NIH, recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium. Researchers randomly sample 50 teens and record their daily intake of calcium. They find the sample mean is 1,198 and the sample standard deviation is 411. Can we conclude that teenagers do not get enough calcium at the 5% level? Okay, so as always, we are starting with our checks. They tell us that they randomly sampled these teenagers. So we do have random sample. And in this case, they sampled 50, which is greater than or equal to 30. So by CLT, again, we know that this is normal. We're going to make that assumption and move forward. Our null, the mean, the desired intake is 1,300 milligrams of calcium. Researchers are concerned that teens are getting less than that. And our alpha is 0.05. Okay, so again, I didn't do a picture on the last one. Let me do a picture again, just to remind us of what we're doing here. So the mean is 1,300. That's kind of the target. Our evidence is showing that teens are at 1198, so something below that. And again, researchers are concerned that they're not getting enough, that the average is below this. Okay, so what we're doing again is we're finding the area of this and determining the probability of that happening by chance. That's our p-value, okay? So let's go ahead and do that, and then I'm going to come back and talk maybe a little bit more about the picture when we do our analysis. So 1198 minus 1,300 divided by the standard deviation of 411 divided by the square root of 50. And that gives us a t-value of negative 1.75. So again, we're going to use positive 1.75 here in the chart. And our df is 49. All right, so we've got a df of 49. We are looking for 1.75. Let's go ahead to the chart and find that information. So let's erase this so we don't get confused. We'll erase this. Okay, so a df of 49, we don't have 49 in the table. We have 40 and we have 50. We always want to be conservative when we're doing this. We want to basically kind of underestimate. So in order for that to happen, we're always going to go up the chart to the smaller t-value. So instead of 50, even though 49 is only one away from that, we're going to actually drop back to 40. So we're going to look in the 40 column. Again, we're looking for 1.75, and 1.75 is right here to right here, which is between 5% and 2.5%. Okay. Now, again, I know that those values are not the answer because they're not the values in the chart. It's something greater than or less than. All right, so going back to the problem. So P from the table is greater than 0.025, less than 0.05. So again, in this case, it is less than alpha, right? We've got a range of values that is less than 0.05. So in this case, we do reject the null. So we reject the null. There is convincing evidence. There is convincing evidence that teens are not getting enough calcium. Not getting enough calcium. In other words, it's less than 1,300 milligrams a day. Okay. So just quickly, again, kind of just to wrap up the process before we move into proportions. So when we find that p-value in this case, between 2.5% and 5%, what we're saying is getting those results by chance would only happen at about 2.5% to 5% of the time. In other words, there's a very, very low probability that our results are just happening by chance. There's something to these results, and that something is that we have convincing evidence that teens are not, in fact, getting enough calcium. Okay. Again, if we had found that P was 20%, it would mean that there's a 20% chance of getting those results by chance. Well, then that's a fairly high probability that it just is a fluke or a chance thing. We couldn't come to the conclusion that teens are not getting enough calcium. Okay, well, let's move on and let's move into proportions now. And so very, very similarly, similar process. The difference here is when we do our checks, we're again going to look at random sample. We will often look to make sure that the population is small enough, that the sample size is small enough compared to the population. Now, again, and I said this in a previous lesson, we don't want to therefore assume that smaller sample sizes are better. We want big sample sizes. It's just that if we have a large sample size, we may not be able to use this process. If our sample size is too large compared to the population, there may be a different procedure that we have to use. But ideally, you want the biggest sample size possible because that's going to give you the data that's closest to the population. The third one, we don't really, that's just kind of a given that the populations are divided into two categories, and so we don't worry about that one. But the third one is definitely important, that n times p is greater than or equal to 10, and that n times 1 minus p is greater than or equal to 10. I believe, again, this textbook actually uses 5. I'm accustomed to using 10, but I do believe this textbook uses 5 for that value. Okay, so we state our hypotheses. In this case, now because we're using proportions, we're looking at p equal to the initial population value, and then our alternative is that, again, P is either less than, greater than, or just not equal to P0. We choose our alpha value, and again, that's typically going to be the 0.05. Now, for proportions, we always use Z. And Z, again, is just going to be P hat, the sample proportion, minus the population proportion, divided by the square root of P sub 0 times 1 minus P sub 0, all over N. We'll use the Z table for this to find P. All right, so a lot of similarities in the interpretation, the conclusion, exactly the same as what we did before. All right, so let's go ahead and look at an example of this. Michael claims to be an 80% free throw shooter. In other words, he makes 80% of the free throws he attempts. Larry believes it is less than 80% and challenges Michael to prove it. Michael takes 50 shots and makes 32 of them. What conclusion can be made at the 5% alpha level? All right, so let's go through our checks here. So is it random? Well, it doesn't say that, but if Michael's just going to go up to the line and take some shots, we're not doing anything special. We're going to call that random. Okay. It's as random as any shot would be, right? I mean, I don't know how you have a random or not random free throw shot, but it's as random as it's going to be. Here it is. Is the population at least 20 times larger than the sample? Okay. Well, in this case, then, if he's going to take 50 shots, we would need for Michael to take more than 1,000 free throws in his basketball career, whatever you want to say that is. So I think we could assume that. So assuming that Michael has taken more than 1,000 free throws, and that would be anywhere, right? Now, the fact that we know his free throw shooting percentage, maybe he's a pro, college, something like that. He's probably taken a lot of free throws. We're going to assume that that's true. And then we want to make sure that 50 times 0.8 is greater than or equal to 5. It's equal to 40. So absolutely, that's greater than or equal to 5 or 10, whichever threshold you want to use. And then 50 times 1 minus 0.8 is equal to 10. And that is greater than or equal to 5, or again, 10 if you want to use that threshold. All right, our alternatives, H sub 0, probability, or the proportion, is 0.8. And Larry is accusing Michael of being less than an 80% free throw shooter. Our alpha value is 0.05. Now, in this case, if we look at the formula again for Z, we need to know the sample proportion, the population proportion, and N. We know the population proportion, P sub 0, that's 0.8. We know N, that's 50. What we don't know is P hat. But we can find P hat, right? Because P hat is simply the proportion of free throws that Michael made in this particular sample. Out of the 52, he made 32, out of the 50, he made 32. His proportion for this sample is 0.64. So that's our P hat that we're going to use. So now we can go ahead and find Z. Z is that proportion, 0.64, minus 0.8, divided by the square root of 0.8 times 1 minus 0.8, divided by divided by 50. And that gives us a Z value of negative 2.83. Now, again, this is the Z table. I don't have a copy of this to show. I forgot to include it in the notes, but this is the one where you're going down the column. You're looking for negative 2.8, and then you're going across the column to look for 0.03, and then that's your value in the table when you cross-reference those. In this case, we should find that P is 0.0023. Incredibly small percentage, 0.2%. So again, remember that that's saying is that the chance that Michael only made 32 out of 53 free throws, assuming that he's actually an 80% free throw shooter, the probability of that happening by chance is 0.2%, incredibly low. All right. So in this case, because P certainly is less than alpha, we reject the null. We have convincing evidence. We have convincing evidence that Michael is less than an 80% free throw shooter, is less than an 80% free throw shooter. In other words, Michael is overstating his abilities. He doesn't actually make 80% of his free throws. He makes something less than that based on this data. All right, let's do another one. And we will finish up with this. All right, according to the National Institute for Occupational Safety and Health, job stress poses a major threat to health workers. A news report claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. Managers of a large restaurant chain wonder whether this claim is valid for their employees. A random sample of 100 employees finds that 68 answer yes when asked, does work stress have a negative impact on your personal life? Do these data provide convincing evidence at the 0.1 significance level that the proportion of all employees in this chain who would say yes differs from 0.75? Okay, so we've got a lot of information in here, a lot of words, but basically what we have is a random sample of 100 employees. News report claims that 75% of employees feel stressed. And this particular survey of 100 found that 68 of those 100 answered yes. So again, we're going to have to find the proportion from that. And we're going to use alpha equals 0.1. And the differs from, this means that this is two-tailed, right? This means could be greater, could be less than. Does it differ from? All right, so our checks. We have a random sample. They tell us that. It says a large chain restaurant. So we're going to assume there's lots of employees. In order for this to work for a random sample of 100, we have to assume that the total number of employees is greater than 2,000, which again, for a large chain restaurant, that's not unreasonable. And then we have to make sure that 100 times 0.75, which is 75, is greater than 5 or equal to. And then that 100 times 1 minus 0.75, which is 25, is also greater than or equal to 5, or again, 10 if you use that threshold. All right, so everything checks. We're good to go. Our null is that P is 0.75. Our alternative is that P differs from, is not equal to 0.75. Alpha in this case has changed. We're going to use a 10% significance level instead of the typical 5%. And again, we need P hat. We need the sample proportion, which is just simply the 68 employees who responded yes out of the 100 employees total. And that is 0.68. All right, so Z is 0.68 minus 0.75 divided by the square root of 0.75 times 1 minus 0.75 all over 100. And that gives us negative 1.62. From the table, if we go to the table for Z, we get a value of 0.0526, which this is our p-value, right? Initially, but remember that needs to be multiplied by 2. So right now, it looks like, hey, we're less than alpha. We have evidence to reject the null, but because this is a two-tailed situation, we have to take that value and we have to multiply it by 2, which gives us 0.1052. And suddenly, P now is greater than alpha, and what looked like we were going to reject the null, we fail to reject the null. So really watch for that. It can make a difference We fail to reject the null. We do not have convincing evidence. We do not have convincing evidence that the workers in this chain differ from I'll just say differ from the study. Okay. Their stress levels are not necessarily any different than those found in the study. All right, well, that is it for this lesson, finding or doing hypotheses tests for one sample mean and one sample proportions. In the next lesson, we're going to get into how to do the same idea for two samples. How do we make a comparison to determine if there's a difference between two different samples and their means or proportions. So with that, thank you very much for watching, and I look forward to seeing you in the next one.